Well, g'day, it's Charlie ZL2CTM. Well, I just want to do a final video to wrap up the SWR power meter. It's pretty well done now, so I don't think I'll be doing anything more on it. So what I just wanted to cover off on today was the circuit that I settled on, and then just a quick overview of the software and some of the decisions I made with that. So what we can see here on the display here is this is the detector, so to speak, I guess. We saw that directional coupler from a previous video, so that's feeding in our reverse voltages coming on the left hand side, and on the right hand side is our forward voltage from that directional coupler. I've got the two 8307s mounted in another old Altoids tin there, just to try and minimize any external interference getting in on those two devices. We'll look at the circuit just in a sec. So the two 8307s, you'll recall I purchased 20 of those from AliExpress. 20 of those in New Zealand dollars was $5.89. So I think US, that's a couple of dollars off that. But you know, $6 for 20 is, I thought, pretty cost effective. They were surface mounted devices, so on their own they were too small to do anything with. But with some of these very simple little breakout boards like this, it was just a matter of quite easily soldering to that and then being able to then gain access to the pins a lot easier with this, like this little breakout board here. And that's what we see down in there. So the circuit itself, what I settled on was pretty well out of the spec sheet. So that's pin 1 through to pin 8. Nothing overly special there. The 4.7 ohm resistor and the 100 nanofarad capacitor, like I say, straight off the spec sheet, and the output with the 10 nanofarad capacitor. Inputs coming through a 100 nanofarad. As we saw on the previous video, I settled, or I was thinking about either having a 15 or a 20 dB pad on the input up here, just to make sure that at the high power end of the measurement range I wasn't going to be exceeding the 17 dBm maximum rating for the 8307. I did settle in on the end on a 20 dB pad, and what that allowed me to do is to run this all the way up to, in my shake here, 100 watts. So 100 watts through to the dummy load was presenting at the input port here on the forward voltage. In fact, I'll go back a step. The output of the coupler was producing 25 volts peak to peak, which turns out to be, if we do the maths, 32 dBm, which is in excess of our 17, but 32 dBm minus our 20 dB pad comes out at 32 minus 20 equals 12 dBm. The maximum rating is 17 dBm, so I was good to go there. So suffice to say, this particular circuit here is good for from notionally 0 through to 100 watts, which is what I was after. I'll explain in a sec. Certainly in the software, there's a couple of little trim pots down there. The little blue things here, they're just providing a variable voltage between 0 and 5 volts for the software to provide a calibration for, one is for the power reading and one is for the SWR reading, just to make sure that things were spot on. Because the approach I took, if I was to key that up, just making sure I'm on dummy load, so we're keyed there, 7 watts, crank that up a little bit more. I would take the measurement on the O-scope, and the O-scope's monitoring the output of the dummy load, or the input, more the point, the dummy load, and then it's just a matter of making sure then that that the reading on this display was exactly spot on. So I did that for both the power and then also measuring what the forward and reflected voltages were for the SWR, doing the numbers and then making sure that the software was correct, maintaining consideration of the calibration. So that's what those two little pots there for. As an aside, I bought 30 of those for $3, again from AliExpress, so that was not a bad buy at all. Okay, so the only other thing I decided to do, or elected to do and tried to do, was a little bit of shielding, just to try and minimise interference between the forward and the reflective side of the house. So there's a copper board there, you know, the solid copper board cut for the spine, and then through the middle there you can see the Pi 20 dB filter there. So there goes the two 68 ohm resistors on either side, and then through the middle, so there's a hole cut in that board there, passing through is the 240 ohm resistor. So there's a 20 dB there and a 20 dB on this side as well, feeding into the input of those two 8307s through a 100 nanofarad capacitor. The red wires there are the VCC wires, and then they all go through, and the orange ones are the output, all go through some feed-through connectors there, which were very nicely given to me. Those are 2.5 nanofarad feed-throughs, so just to give a little bit of additional decoupling on the DC output from the 8307 to 10 nanofarad capacitors, one there and one there, just on their sides. Those two DC voltages then get fed into, in fact I'll leave that open, get fed into the two analog, let's come down a bit, through to two analog pins on the Arduino. No external amplification, i.e. there's no additional op amps, that is feeding straight into the Arduino. Right, I think that's probably all I'm going to cover off on that. So in terms of actually arcing it up and doing some experiments, what I did is I decided to use, and I'll say this now, if people are not using and you don't have access to Microsoft Office, the Google Docs has got some really good stuff, and I use the Google Sheets program here over and over again. It's a spreadsheet program like Excel, but it's very easy to use. It's great. So what I've done here is I've thrown in a range of powers. I worked out what I should be seeing on the oscilloscope as the voltage peak to peak. So I made sure that what I was actually getting at the dummy load was what I expected to be for the power. So I've just varied my output transmit until I got the right voltage. And then I logged the voltage coming out of the 8307. And then I'm just now plotting watts, or this column, with the forward voltage column, and I get this output plot here. So if you look at that, you can sort of see straight away that it's not a straight line all the way from notionally, let's say 1 watt all the way through to 100 watts. I've decided that it is pretty well a straight line from 40 watts through to 100, and I've decided that, and you'll see that in the software in a sec, that it's pretty linear as far as I'm concerned in 5 watt increments. So from starting at 20, from 20 to 25 is pretty well straight, from 25 to 30 is pretty well straight, 30 to 35, and then 35 to 40. So I've divided that up into those 4 semi-straight lines, and then a big straight line from 40 through to 100. For values below 20, what I've elected to do is I didn't try and come up with a formula to describe what that line is. All I've decided to do was, well, I measure the voltage coming in, and if the voltage is anywhere between 1.86, for example, 1.97, it equals 1 watt. If it's between 1.97 and 2.17, 2.017, it's 2 watts. So just for a simple lookup table using if statements, again, right or wrong, I just assign a wattage value based on a small range of voltages. And honestly, for what I do here in the shack, that's good enough for me. Now, incidentally, this straight line here, let's just have a very quick look at the maths for that. So for the software to work, we want to have an equation that allows us to plug in a measured voltage, and the equation will spit out in this particular case, a wattage value. So it's fair to say or it's correct to say, that we know this point here and we know this point here. So mathematically, if we just come out of that and just go and have a look at the bit of paper, this is what we have here. So we've got 2 points on the graph which are known. So we know that at 40 watts we have an output value of 2.3. So that's our y1, x1. That's a y-axis. That's the x-axis. And we have at the other end, at our 100 watts end, we have a value of 2.37 on our y-axis. We'll call that y2. And then, as we just said, on our x-axis, the power axis, we have an x2 value of 100. So we know those 2 points. So this is the expression that you can apply to a line that passes through 2 known points on a graph. So y is our unknown, minus y1 over y2 minus y1, knowns. And x minus x1 over x2 minus x1. So those x's and x1s and x2s are these values here. So y2, y1, x1, x2. So very quickly you can start to plug in what you do know and then rearrange things in terms of what we don't know. So that's exactly what I've done here. So I've now plugged in what I do know. So y minus 2.3, because that's what that's what y1 equals. And I've plugged in y2 and y1. And on the right hand side I've plugged in what we know for x1 and x2 and x1. Now the expression we've got here, this is the expression. We want to express that in terms of x, because x is our unknown, somewhere in here, our unknown power as a function of a measured voltage y. So what I'm going to do now is I'm going to start moving things left and right across the equal sign here to make x the subject. So for a start we can move this expression here, so 100 minus 40 equals 60. It starts on the bottom side on this side, it moves to the top side on the left hand side. In terms of a simple way of moving it. What you're effectively doing is actually multiplying both sides by 60, but it's quick enough just to move things that way. That's where that 60 comes from there. 2.37 minus 2.3 equals 0.07, and that's why it's sitting there. And the right hand side, because that bottom bit's now moved, we're just left with x minus 40. I'm just going to rearrange things to keep it in line with what you typically normally see, and make x on the left hand side and then everything else on the right. So y2 minus y3, 60 over 0.07. If we add 40 to both sides, we'll make that disappear, which is exactly what we've done here. So x now equals that expression plus 40. And that is what gets fed into the software. So if I was just to jump up into our program, and if I just move that up to there, we can see there, let me just zoom up a little bit. Sorry about that. That's exactly what we see here. So for in our lookup table, anything greater than 40 watts, so in other words the voltage is greater than 2.3, greater than equal to 2.3, that's our function. So our y, our measured voltage, minus 2.3 times 60 divided by 0.07 plus 40 gives us our power, and that's what we're actually displaying on the display. I'm not going to go through the software line by line. I'll certainly put it up online. Like I say, I'm not a software engineer, but it works for me. I've decided to do an average, so every time I loop through the main loop and I take a measurement reading for our forward and our reverse voltage, I'm placing those into an array. The array is 10 bins wide, so I'm taking an average over 10 samples, and then on the 10th time through we then add it up. So we add the bins from 0 through 9, divide the total by 10, gives us an average over those 10 bins. Now I mentioned before those two trim pots. Those are also being read each time through the loop. So we have our power calibration and our SWR calibration. And what I'm doing with those two voltages there, what I did find, and I don't know if I explained that yet, so I'll repeat myself now anyway. When I was putting together this, I had the circuit being powered from the USB port as I was doing the software engineering. And I noted that when I disconnected from the USB port and I went on to the standalone 7805 voltage regulator to run both the Arduino and the two 8307s, that ultimately the voltage I was reading shifted subtly. So I needed to build in a calibration, a way of calibrating the output to be to take care of any variances in the power being supplied to the overall circuit. So in other words, what we saw up on the screen there was subtly shifting, so I needed a way to compensate for that. So those two 10K pots are just sitting between 0 and 5 volts and outputting that voltage into the analog pins. And as we saw in the software, those two pins are being read each time through the loop, and I'm converting the number I'm reading to a number between 0 and 5. So what I mean by that, so the analog pin on an Arduino will divide whatever it's reading into 1024, or 0 to 1023, quantization levels. So it'll slice and dice whatever it's seeing on the analog pin up to a resolution of 1024. So what you need to do in software is you need to convert that number between 0 and 1023 into something you can actually do something with. So what you could do is you could just convert it into, and what I've decided to do is just divide it into a number between 0 and 5. It's not unusual for people to use 5 because 5 volts is typically the range on the input. So if you multiply whatever you're reading by 5 divided by 1024, you will end up with a number that ranges between 0 and 5. I was quite happy with a number between 0 and 5 because I wasn't seeing much more, I wasn't seeing a huge variance there in the voltage I was reading coming off the 8307, so that was fine for me. And that was the case for both the power calibration and the SWR calibration in the software. So that's what's going on just in there. We're just reading those two calibration pots and then applying those to the, in this particular case, to the power, and then later on down the bottom to the SWR reading. So, like I say, I'm not going to go through any more on this. From a display point of view, what I elected to do, again, right or wrong, you know, there's different ways of skinning cats or those sorts of sayings. If I was just to key this up again on dummy load, yes. So this is currently an SWR of 2. So I've got 2 major divisions. And if I was just to tune it off a little bit more, it'll start to grow. So what I decided to do, so coming up on three full divisions, and as we come down. So you can see there, that's the null in that particular case. And our forward power being effectively measured there. So in the end, that's what I've settled on, and this graph here is just straight out power as we climb up. So 29, 68, all the way up to 100. So I'll just unkey that. That's what I've decided to do for the 2 bar graphs down the bottom. I initially had forward power and reflected power as a pseudo split needle, but I decided that I was just quite happy to have the power being read out as a pure number, and then just a bar graph, I guess just as a quick sort of visual reference of what the power was between 0 and full power, and then to have an SWR graph that I could just sort of see sort of dipping backwards and forwards with a numerical number at the top. So that's what I've settled on. You know, everybody's got their own different ways of displaying that, but like I say, that's what I've settled on. Okay, well, I think I've rambled on long enough on that, so I'm not going to do any more on this particular project in terms of software / hardware for now. I just need to put some thought into how I might mount this. Knowing me and what I like, I'll probably keep it al fresco and a little bit open. So I might even work out a way that this is all nicely mounted and then sits on top of the lid of the Arduino, and then that sits up just up here on the shelf unit. So I suspect that's what I'll probably do, because that's what I enjoy. Anyway, I'll say 73s there. I think, like I say, I've rambled on long enough. Hopefully that was of interest, and maybe a little bit of an insight into the approach I took and some of the thinking involved with that. I will certainly put all of this material up onto the blog, and people can do as they see fit with it. Anyway, I'll say 73s and put some thought into what to do next. Cheers all.